Hi, my name is Alberto Sonino, and I'm going to give you a brief presentation of twins, BFT systems made robust. So this is a joint work with a lot of people from Facebook, Nogi, and Diem. On the research side, we have Benno, me, and Dalia, and on the engineering team, Andre, Dimitri, Zikin, and Ivory. So the engineering team is really what allowed us to take the research and make it to a production-ready system. So here is the settings. Pretty usual. We have a set of nodes. That's the green one. And among those nodes, we have some which are bad. They're Byzantine. More than 2f+1, so more than 2/3, need to be honest and follow the protocol. And we can tolerate at most 1/3 bad nodes. So that's pretty classic. And here is the game. So we have our set of nodes that comprise the Byzantine nodes and users. Users want to submit transactions. They would create a transaction, send it to the set of nodes, which form a distributed system. The distributed systems will run some kind of consensus protocol, execute the transaction, order it, whatever order, and then finally, if they decide that everything is okay, they would commit the transaction and persist this to storage. So this is all pretty classic, and here we are interested in the consensus protocol that runs among those nodes. So those protocols have been there for over 30, 40 years before I was born, but only recently it seems that we are getting interest and fundings to make them production ready. And that's changed quite a bit of the game. So when we take the example of DiemBFT, which is a production-ready BFT system, you can see on GitHub that it has over 10,000 Git commits, 200 contributors that submitted, I think, something like 8,000 PR over the past years. So that's quite a lot. That's a big software project. But again, there have been many big software projects as well. And what makes this complicated or different than others? Well, it's the presence of Byzantine adversaries. So the questions, which is an engineering question, was how do we write unit tests or integration tests and make sure that our software does what we expect to do, even in the presence of Byzantine adversaries? And by the way, what are those Byzantine adversaries? And it turns out we didn't really have a pretty good answer to that. Byzantine adversary can do pretty much whatever you want. So it was not really clear how we can achieve that. And that's the motivation behind twins. So first of all, twins is not a formal verification tool. It has absolutely nothing to do with that. It's completely orthogonal, and it takes a very pragmatic approach. So here is how twins work. Twins has two capabilities. First, it can create multiple copies of the same nodes. Let's say we have 7 nodes, the one you see there, A, B, C, D, E, F, and G, out of which 5 needs to be good, and F and G, the 2 last, are Byzantine. They're the bad one. Well, the first capability of twins is to create twin copies of the Byzantine nodes. So we don't only have F, we also have F prime, and we don't have G, but we also have G prime. So what are twins? So twins are the same instantiation of their original brother, but they keep the same cryptographic key, so they're very distinguishable to the eyes of anybody else. And when they're elected as leader, well, both twins are elected as leader at the same time, since they have the same cryptographic keys, but they all propose a different payload. In fact, the payload is random. So that's the first capability of twins. The second one is the ability to add network partitions. So we take the network of all our nodes, including the twins, and we separate and partition it however we want. So for instance, here we have partition 1 and partition 2. In partition 1, we have nodes A, B, F, G, and E. So those nodes can communicate with each other, but they cannot communicate. So A, B, F, and G cannot communicate with the nodes of partitions 2. They're isolated through the network. Only E, which is in the intersection, can communicate with any other nodes. So this is how we impose partitions, but they can change on a round-per-round base. So we assume a round-based protocol, and they would be, those partitions would change. We may have partitions that englobe all the nodes for some rounds, and the one as described for other rounds. So why does this help? Why these two capabilities help capturing Byzantine adversaries? Well, the intuition is that twins capture notable misbehavior. The notable ones, I mean, some of the notable ones at least, are equivocation. It means that a leader proposes two conflicting proposals to two different nodes. Amnesia. So typically in this leader-based protocol, we would have good nodes to vote for a single proposal per round and not twice. And amnesia is captured by the fact that sometimes a node may forget that it already voted for a proposal in this round and would vote again. This can be captured through the twins, since both twins can actually vote without knowledge of whether the other twins already voted. And losing internal states, that's very similar. Often we require some lock on voted value to prevent going back in time and not voting for conflicted values. Again, since the twins do not share their internal state with each other, it may appear as both one would keep the lock while the other would lose it. So here is the baseline case. The baseline case is we have 4 nodes and f+1 Byzantine nodes. So of course, f+1 means that we should see easy misbehavior from the beginning. So here is the simplest case, just to have the baseline. We have 4 nodes, A, B are honest, C, D are bad, and since they're bad, they got a twin. So we can set the network partition as there. So A and B are completely isolated. D and C are on partition 1, and D prime and C prime are on partition 2. You can see that if D becomes the leader, D prime is also a leader. They both send a proposal. Remember, proposals are random, different across twins. Well, after a few rounds, both D and D prime will gather enough votes and then commit it. A and C would vote for proposal D, and B and C prime will vote for proposal D prime. So this is very easy, but we can also instantiate more complex attacks. So we took a few known attacks and we instantiated them back as twin scenarios. So we did that for a safety attacks on Ziva, a liveness attack against Fab, a timing attack against sync hot staff, and a non-responsive attack on linear leader replacement. So all of these we instantiated, those are known as already in the literature, but we instantiated them as twin scenarios. And it turns out that twins found the attacks and the bugs within minutes, which was quite impressive. And in any case, within 7 or 4 nodes committed. So it didn't even require a large committee size for that. And next, we also instantiated a new attack, which is against protocol called fast staff. It's a safety attack. And in that case, twins only needed 11 rounds to find the attack with 4 nodes committed. So 11 rounds is only a few seconds. So this gives us a good idea that the intuition that twins work is good. So here is how we implemented it. There are 2 main components for that. The first is the scenario generator. First, we produce all possible partitions for all nodes. Then we assign each partition to all possible leaders, and we find all ways in which the leader partition pairs that we just created can be arranged into R rounds. R is a system parameter here. So already step 1, 2, and 3 are very combinatorial. So it already gives a hint of a weakness of twins here. We have a gigantic number of scenarios to test. Step 4 is we filter some of those, the one that we consider trivial. Again, here is another work in progress. What does trivial means is not necessarily clear. But anyway, once we have the scenarios, we have this the scenario executor. Now we execute them. So we took our nodes, also the Byzantine one, that's D. We take the twin of the Byzantine nodes, and we connect them to each other through a network playground. So we can see that as a gigantic network switch that connects all nodes, and that allows us to enforce the partitions on a round-per-round basis, since it sees all the traffic. And for instance, for a specific round, the network may decide to allow a message from A to B, but not allow the same message from A to C. And so, yeah, this is the big picture. So how we would integrate it into some periodic and routine tests. First, we generate the scenarios. This can be done beforehand. The scenario go to the executor. They get executed, logs are printed, and added to persistent storage. Then if we have more time, well, we would repeat again, generate more scenario, and we execute them until we run out of time, basically. on a fixed time base for every time, for instance, we commit something new to the software. And yeah, so twins run in production, so it's integrated within DiemBFT, so that's a real thing, and it needs your help. So a lot of things are missing actually. Coverage, for instance, as you could see, well, we generate a lot of scenarios and then we filter some, right? Because otherwise there are too many scenarios. So what does it mean in terms of coverage? Are we covering all Byzantine attacks? Are we losing interesting scenarios by filtering? Then deterministic scenarios. So this can be a little bit more tricky. So it turns out the way those softwares are implemented, so the core, the consensus core of every node is asynchronous in nature. It's made of multiple tasks, potentially running on different threads. So it's not because we have one given scenario that we execute once that if we that it's deterministic basically. If we happen to re-execute it another time, we may have a totally different outcome just because of the way the internal consensus score works. So that's a challenge. We like to have deterministic tests. And the last one is guarantees. So what is twin guarantees? Well, we have an intuition that having a twin on Byzantine nodes will capture some Byzantine behaviors, but does it capture all? And if not, which one are we missing? So this is also an open question. So that's it. In conclusion, twins, it's not formal verification, it's a pragmatic approach to BFT testing, and it's the first of its kind. So it's quite a novel approach to BFT testing. And it's in its very early stages, so it needs a community effort. It needs your help to grow and go forward. So if you want to have a look at a full paper, here's the link, and the code is included in DiemBFT. So thanks for listening.